is a target for the upgrading. We're using heating source, high temperature, but we using the heat pump try to get the absorb heat from the low temperature, but output to the medium temperature. So this is we so-called, this is the first type heat pump, usually used for absorption or adsorption, but you need the high temperature heat sources. But another possibility, if you have medium temperature, for example, 80 degrees or 70 degrees, 19 degrees, but you have low temperature emitter sources, you could try to separate this kind of medium temperature into high temperature and low temperature, two kind of heat. In this case, you could upgrade medium temperature to a high temperature. This is so-called second type heat pump. It's a kind of heat transformer. So in this case, the working pairs could be liquid gases, solid gases. This is typically as absorption or adsorption systems. So now what I want to talk is more for soup heat pump for waste heat upgrading. So what's a soup heat pump? I think it's a bridge for the demand and the sources. If we just have a look of the heating sources, so usually that the lower the heat and the lower temperature, you may get a much bigger heat quantity. So in this case, if we try to, this is heat sources, this is temperature, for example. So if we're using heat pump, just to try to upgrade, and then you could try to make the lines up to get a high temperature. In this case, you get a more heat could be used. So in this case, you meet the demand more, because originally, if it's a demand line is here, temperature and heat, but a heating source is here. So if you upgrade and then you come to this line and you get the more possibilities, but you need temperature lift for the heating supplier. So in this case, we have larger temperature lift heat pumps could be possible. This shows the example, whether it's electrical or we use absorption systems. So if we consider super heat pump, you need really high efficiency. So if we use for the vapor compression system, we need high efficiency compressors and also heat exchangers. And also we need to consider high efficiency cycles, how to design the cycles, try to make high efficient. And also for the super heat pump, we need the high temperature lift output. This shows the example. We have a temperature lift about 40 degrees. So if originally heating source is 80 degrees, but you need lift to 120. So then the COP value for different refrigerant will be like this. So in this case, especially if we see between 80 degrees to 100, so this ranging, the water is very, very good to have a more higher performance to compare with normal refrigerant. But originally, such development is very less. And because there is not much research for the high temperature output to generate steam. So in this case, if we want to generate steam for temperature more than 100 degrees centigrade, possibly we consider maybe natural refrigerant, such as water, could be good options. Other options could be the fourth generation refrigerant, like R1233ZE, for example. So this is for the high temperature heat pump refrigerant, actually. And also, we need, for the upgrading efficiency, to get high efficiency, we need a small temperature difference, heat transfer. So this just shows one example. If we have the heating source temperature, TH, we could, and this is the ambient temperature. And we could produce work. And this work to generate a cooling refrigeration to get the refrigeration temperature, TR. So this is a Carnot cycle. If we consider Carnot cycle, heating source temperature as 80 degrees, ambient temperature 30 degrees, and the refrigeration temperature 10 degrees. So ideally, if heating, there is no temperature difference for the heat transfer, then the COP could be about 2. But in the real applications, so we have maybe the heating source, you may have the heat exchanger to have over 10 degrees temperature difference. Here for the ambient, another 10 degrees, and for the refrigeration, if we have 5 degrees temperature difference. So then this COP will be decreased from 2 to 0.69. So this is only for the Carnot systems. So the performance reduction is nearly very, very significant. So in this case, the heat exchange design for the heat pump is also very, very critical. If you try to make high efficiency heat pump. Okay, so small temperature difference heat transfer is request in this case. This just shows how small temperature difference heat transfer is needed. If we have a traditional refrigeration cycle, so this just shows single cycles, but this is one condensing temperature, one evaporation temperature. So this is just to show just waste heat from 30 degrees cooling down to 25, but we upgrade from 50 to 60. So, but you need the condensing temperature, maybe 62. But we could consider if we divide the heat exchanges. So maybe for the evaporate, only one evaporate, but a condenser, you may have 2. This is 2 segment. Or you have evaporate 2 segment and a condenser 2 segment. So in this case, you could make adjustment of the evaporation temperature and the condensing temperature, because this is in consideration, the heat transfer is with some limitation of thermal fluid and heat transfer area. So this is, in this case, what we could see is that this kind of the area, because this is a heat transfer area, it's a not irreversible process for the heat transfer. If you have this kind of 2 segment, you could reduce this kind of area. And in this case, the double condensing and evaporation segment, you could generate, actually the COP could be increased for about 13.6%. Or another saying, we have the so-called intrusive dissipation reduction for about 22%. So this is just to show that how small temperature difference heat transfer design is important for this kind of waste heat upgrading. And also, for the super heat pump, we are not limited for the uses of the huge systems. This huge system may be for 1 megawatt or 10 megawatt or 100 megawatt for the waste heat utilization. But also, we may need some decentralized new equipment. So if to the customer, you need only 100 kilowatt. So in this case, you need to develop some small system or even uses some absorption, or some vapor compression heat pumps or some storage units. And also you need to consider the source is the waste heat, but demand is the heat needed, how to match, depending on the temperature left. And then you need to select the possible heat pumps, whether it's vapor compression, but for the vapor compression, you have different refrigerants. And you have also different type of, whether it's a screw type compressor or centrifugal type compressor, and so on. Also, for the application of the waste heat, in this case, you need some optimization of the network. So in this case, we need some network utilization. Try to make some optimization that depending on the demand, but the source, you have a centralized source always heat, but demand maybe you have different temperature requirement, whether it's for heating or cooling or upgrading or some thermal storage. So this is actually the so-called optimization of network utilization. So now I want to show you for the vapor compression heat pump and our demonstration project. So this just shows for the vapor compression heat pumps. And we used here the evaporation temperature at about 23 degrees and to condensing temperature about 67. This is a normal centrifugal heat pump we consider. But we could also consider if we use two compressors. So because usually for this big system, several megawatt, you need maybe 2 or 3 compressors. You could have one evaporator, one condenser. So then the heat transfer is like this. But if we have 2 condensers, you could arrange like this, but this is only one evaporator. But if you arrange 2 evaporator with 2 evaporation temperatures and 2 condensers and with 2 condensing temperature, it's a so-called 2 segment applications. So in this case, the heat transfer looks like this. And then we designed the whole systems. So, and to using centrifugal compressors. And so 2 segments of evaporator and condenser. And the water sources with heat from 30 degrees. And we take 30 degrees cooling down to 25. And then we take this heat and we heat temperature 55 to 65 for output for heating. And we use this kind of double condensing evaporation temperatures and design equated for COP more than 6. And the heating output is 9 megawatt. So this is our design. And we applied this centrifugal compressors. And this compressor actually we're using 2 stages and refrigerant that's 134A. And this actually was manufactured by Gree, the biggest air conditioner manufacturer in China. So this is 10 megawatt. And we did the testing. So this is cooling down from waste heat 30 degrees. And we take it and then we upgrade. This is nearly 49 degree upgrade to 60 degrees. So this is the COP. So based upon this, and then we move this machine to the Lear application. That's a Lear project. And in the North China, Liaoning, and Anshan Steel company, they have the waste heat about 30 degrees. And but residential houses, they need about 60 degrees centigrade hot water for heating. And it's just 180,000 square meters and used for the heating area. So actually this is the results. We have the source temperature 32.4, we upgrade to 62.6. This is nearly about 10 megawatt. And the electric consumption is here and the COP value is 6.67. And this is actually the very good project. So the payback period is only about 1.7 years. So after this operated in the year 2017, and then the customer, then they are agreed and then pay additional 5 projects, the similar 5. And in this case, we demonstrate the first one, and then because the payback period is less than 2 years, then the customer is very happy to take more, another 5 units. So then in the year 2018, so 6 units in operation. So this is a very good demonstration for the wind heating. We take the waste heat from the steel industries, but only about 30 degrees centigrade, but upgrade to 60 for wind heating. Also, this technology could be used for ground source heat pump because it's very similar, because ground source, you have the temperature maybe about 20 or 26 degrees centigrade, but we upgrade to actually upgrade to about 40 degrees or 45 degrees and then use the for heating. So this is a project, small one, also using centrifugal compressor, and this is used for 10 square meters. the building heating in Shanxi province. My second example will be absorption heat pump and demonstration. So Shanghai Jiao Tong, we did some research for the absorption heat pump. Especially, we did the complete absorption cycles, and whether it's using the type 1 heat pump for the increased heating output, but we have a high temperature heating source. But for example, if it's 120 degrees centigrade, and we take heat from the low temperature, maybe ambient, maybe 30 degrees, but you upgrade to about 80, something like that. So this is normally we try to get a COP 1.7 or 1.8. So this case, because you take nearly about 70% or 80% is from the waste heat. Also, we tried to, if you have the high temperature heating sources, and you could have a second, if you have the high temperature heating sources, you could have a double effect heat pump. Try to get the COP value 2.5 or 2.6. And we also made some investigation of second type heat pumps. Try to get 80 degrees with the heat upgrade to 120, something like that. But in this case, the COP may be 0.4, 0.5. So it's a kind of heat transformer. But for Lee applications, and we tried this kind of larger temperature lift cycles. And also we try this kind of 2 segment units. Try to get 2 evaporation temperature and 2 condensing temperature like vapor compression systems, and try to get the efficiency increased. So it's a 2 segment heat pump of absorption. Also, we tested a combination of vapor compression system and to get about 80 degrees hot water, and then upgrading 80 degrees to 120 by a second type heat pump. So in this case, we could using air source heat pump to generate steam. So these are all our researchers for the absorption cycles. So then we collaborate one of biggest company, so-called Shangliang, and so in China, in North China, Lanzhou. So there is actually electric power stations. So original unit, that's a electric boiler, and you get the steam and come to the gas turbine, steam turbine, to generate the electricity. But some steam, and then the condenser, and here the condenser, and then you have some waste heat and in the cooling water tower. So usually a lot of heat released in the cooling water tower. But for the heating applications, the customer, so normally 50 degrees come back, and then we're using just introduce steam from the gas turbine and try to heat this kind of heat exchanger to get about 100 degrees, 105 degrees for the central heating. So this is the original one. But that area increased a lot of new buildings for heating, but there is no additional heating units. So in this case, we proposed whether it's possible, we try to absorb heat from the cooling water tower. Just introduce this kind of absorption heat pump and try to get 35 degrees from the cooling water tower. Originally come to the air, but now 35 come to the absorption heat pump to the evaporate, and then 30 degrees back. And then we upgrade this with the heat from the central network back to 80 degrees. So this part is taken by absorption heat pump. So 80 degrees to 105, then we introduce the steam vapor for heating. So this is actually new configuration for the upgrading. And this is a big project. This is 290 megawatt. And we have 6 units of 45 megawatt absorption heat pump. So this was very successful demonstrated there. And this just to show how we did. So 35 degrees waste heat from cooling water tower. So we take the heat to the evaporate, and you get 30 degrees out. But we take the heat from the network and then try go absorption, just the absorption heat and condensing heat, and then you get about 80 degrees to the network. So this is in the layer, but you need about 120 degrees steam for the generation. So, but we want to increase the efficiency. So in this case, we design this kind of yeah, 2 units, just 2 segments. Try to make a more high efficiency. So this high efficiency, that's 1.75. So it's really that's a high efficiency, and this just shows the main performance. So after that, we need consider the more for the network the utilization of waste heat. So based upon this figure. So not only limited to centralized for superheater pump, but we need some distribution for the customer usage if it's a small unit. So we developed so-called variable effect absorption heat pump. So if we have lithium bromide water, single effect system for cooling, you need about 85 to 95 degrees centigrade. And so this is just for the COP value for the single effect. But you have a double effect. If it's a high temperature by steam, 140 degrees, so it's a high kind of double effect system. But if you have the heating source temperature between 100 to 140, there's no product. So what I wanted to build is to build it like this. Try to make this kind of connection. So called a variable effect. So when the temperature is below 85 degrees, that's single effect. When it's 85 to 140, it's a variable effect. So 140, that's a second effect. That's a double effect. So in this case, we developed a very specific unit, try to make high efficiency uses of this kind of absorption systems. So this just to show what we tested. For example, if you have the steam temperature about 120 degrees centigrade, so you get the cooling COP is about 1.05. It's not 0.7. So this is just one example. Another example, we build some system of silica gel water absorption chiller. Try to consider the uses of 55 to 90 degrees. So if temperature is very low, so whether we could using this waste heat for the utilization for cooling. So in this case, we use absorption chillers. So this is this cycle, so-called heat and mass recovery, that was invented by me, and now it's we have a lot of commercialized product. So this silica gel water absorption chillers, now we have considered for the uses of data center cooling, because they have waste heat between 50 to 60 degrees hot water to cooling the chips. And normally it comes to the cooling water tower. Now we could make a good use of that to produce 10 to 20 degree chilled water. So a COP is between 0.35 to 0.5. So now we are trying to make good uses of this kind of product, try to collaborate with chip cooling, especially for the data center. Also, we invented ammonia water absorption ice make. So here, so if you have the waste heat, exhaust gases from diesel engine, so this is the waste heat, the temperature of exhaust gases, we could get minus 20 degree freezing, and the COP could be about 0.4. So we designed the whole system, and this is the unit of 30 kilowatt. And to generate minus 10 degree, you get a COP. It's really high. But in this case, you need the best heat recovery design for this kind of cycles. And also we developed a kind of heat pump to using water as a refrigerant for steam generation. So if we have the heating source of waiting waste heat, so we output between 120 to 150 degrees centigrade. So this just to try to make good uses of water as a refrigerant. So we build the system, and it's especially the most important is a good design of the compressor. And we use screw compressor, but you need the inlet cooling by ejection of water, spraying. So actually this shows that with the electrical, here if it was 80 degrees upgrade to 115 degrees, and so the COP is 5.7. And if we're 80 degrees to 120, COP is 4.5. So it's a very good value. And we built this system. After we built, so we see it's a high efficient using natural refrigerant. Then we consult the industry people. They say, Professor Wang, so heating is good, but if you share this kind of heating, the cost is not much. It will be good if you could generate steam vapor, just share steam vapor, then you get a high price. So in this case, then we consider another possibility. So if we have a heating source or waste heat at about 80 degrees, so we could using this kind of flash tank to get 80 degrees water. It come into the flash tank, and then we're using compressor to take, normally here the vapor pressure is in the vacuum, about 500 millibar. So we're using the water compressor to compress to high pressure, maybe with a pressure ratio about 4 to 6. In this case, you could generate 120 to 150 degrees centigrade. So in this case, so this is originally designed for very high temperature heat pump using water as a refrigerant. But we use this condenser. But now we want to consider, okay, not like this, but we could produce this kind of steam directly come to the customer. So in this case, we could provide another option of heat pump to generate steam. So in this case, we're using air source heat pump and with a water vapor compressor. So air source heat pump, you absorb energy from the ambient to produce about 80 degrees hot water. You could have a COP about 3, for example. If you upgrade steam to high grade steam by this kind of water vapor compressor, and you could possible to get temperature lift for more than 100 degrees centigrade. So because if the ambient temperature is below 20 degrees, but you produce 100 or 120 degrees, so temperature lift is very high. So in this case, we try to get high efficiency with a combination of the water vapor compressor with air source heat pump. But in this case, we're using a flash tank. So try to absorb, get evaporation of vapor, and then coming by the compressor. So this just shows this to produce steam, and then we use this steam produced in a factory to produce alcohol. So this alcohol could get a concentration 70%. So this is already operated for more than 1 year. Because after 1 year operation, the customer is very happy now. They want to make investment. They say, so this generation is about 300 kilowatt. It's not a big high. They need about 1 megawatt. So this is, in this case, we need to produce more high capacity compressor, and in combination with heat pumps and solar energy, and try to produce steam. And also there is a customer that need thermal storage, so they come to us. But Shanghai Jiao Tong, in the last years, we produced a lot of researches for the PCM to use a hydride Zat composite And for example, the PCM 60 degrees centigrade, we use a sodium acetate trihydrate, or PCM 90. So in this case, we try to get the PCM in collaboration with expanded graphite for the very good heat transfer, and then so manufacture it and then put it into the real uses. And this just shows how we make the heat exchangers in combination with the PCM, but it's mixed with expanded graphite. And really, we made it like a battery, so we call it a thermal battery. So in this case, you could easily to make it blocks, and this is our last product. And then used for demonstration in Beijing, and it's a 2 megawatt hour unit for the thermal storage, because there they have a bigger electricity price ratio during the day and during the night. So in this case, what we tested in Beijing, that the payback period, that's 2.8 years. So now the company already, they produced the capacity from 10, 20, 50, and 100 kilowatt hour. And we designed about a 50 degrees, 60 degrees, or 19 degrees unit. So in this case, not only used for the heating, electrical boiler heating, this is for the thermal storage, or also for the off-peak uses. Also, we use it in Tibet area for the solar thermal storage. And for the industry with the heat uses, we need to consider networked utilization. So we have a wide selections of industrial heat pumps. So in this case, we could have a lot of opportunities of refrigerants. So if it's operated the evaporation temperature or condensing temperature, so they have the, based upon the source and the demand, you need to consider which refrigerant is better. Or we could use vapor, that's a absorption system. So the type 1 or type 2, whether it's a lithium bromide water or ammonia water. So depending on the heating sources and heating demand. So also the heating sources available. So in this case, you have your options, or also consider for the absorption systems. And in this case, if we consider for the vapor compression, so based upon the heating sources here, this is the heating source side, and we have a selection of refrigerant. And the system, whether you're using single stage, 2-stage, or cascaded systems, and so different type of compressors, and then you get a various kind of output temperature. So in this case, you have multi choices, for the heat pump. So I think in this case, what we want to give for the customer or for the leaders to know how to make this selection. And also for the sorption heat pumps. So also we need to tell the people how to make a select choice of adsorption heat pump or ammonia water or lithium bromide water absorption heat pump. It's mainly depending upon the heating source temperature and also the demand temperature. Also, we need the design for the so-called global optimization based upon super heat pump. So in this case, so this just shows with the supply side of the heating sources, but you have various kind of demand. So it's a kind of network, and you need optimization for the network. And also in the design, you have some, we could apply using so-called in-choice method. It's a very similar to the pinch analysis, and usually by the heat transfer, we just see the high temperature side fluid and the low temperature side fluid, and the area is just a kind of so-called entropy dissipation. So in this case, it's very easy to be understood and to using TQ diagram for the analysis. And also we may have some mathematical models, try to using mathematics for the whole optimization. So after this project, so this is a general figure, but we also produce the technology roadmap for low-grade heat utilization. So this try to consider the low-grade thermal energy, waste heat used for heating, power, or cooling, or storage, or transportation. So in this case, I published one book, so-called waste heat network utilization. And based upon here, we did some analysis. So using this kind of interesting method for the optimization. And this is what we had for in Lanzhou for the electric power stations, or for the this is just the cooling water tower. And here you see, originally the turn water at about 50 degrees is heated to 105 degrees centigrade. But we're using steam condensing for the heating. So in this case, you have a lot of heat transfer dissipation. So it's a kind of, losses. So, but if we use absorption heat pump here, so then between this kind of 30 degrees and to 80 degrees, because we have a heat transfer with the float, we're using 2 condensers and 2 absorbers. So then the area is very small. And for the steam, because we have to generate and to make exchanges with the steam vapor. So the area is here. So only when it's more than 80 degrees if you want to heat it. So because this heat pump only upgrade to 80 degrees, so but this part is steam. So you need the steam heating. So in this case, what you could see that you get so-called intraocean dissipation, get it nearly lower, and the reduction about 57%. And we made analysis for the first law analysis, efficiency increase nearly about more than 30%. So this is just to consider to using intraocean method or network utilization, to using similar to pinch analysis, or we're using TQ diagram for the analysis. And also we had another project when I visited Singapore. And in Singapore, there is a company called Sembcorp. And in Jurong Island, there is a petroleum oil refining company. And they're using the supply heating. But this is, in this case, there are a lot of waste heat and then come to the sea. And this is originally framework, but we made some analysis by T-curve diagram and to see the heating, hot fluid, so coming down the temperature, but you have several thermal fluid, but the temperature like this. So in this case, the area between that's a kind of dissipation of interest. And then we try to introduce, just to make a little bit changes. So if you look, this looks very nice, but if we look here, we introduce absorption chillers, single effect lithium bromide absorption chiller here. So then what do you see that the thermal fluid coming down and here, and we reorganize some cooling fluid like here. So in this case, you get a dissipation of interest very low. And so this project then demonstrated in Singapore, and so with the waste heat recovery about 8 megawatt. So we produce 5.6 megawatt for cooling. So in Singapore, cooling is very important. So it's a very good project. So we are lucky that in the last 4 years, when I finish project in China, and then take the opportunity, have a project in Singapore. So this, we have the payback period, less than 2 years. So it's a very good project, and also with a high capacity of absorption chillers. So based upon this research, I have some conclusion and perspectives. So superheat pump, usually it's a larger capacity, high efficiency, larger temperature lift, and it should be economical and it should be suitable for centralized waste heat utilization. And we could using vapor compression heat pump, for example, upgrade from 30 to 60, or using absorption heat pump from 35 to upgrade to 80 degrees. So this is my two projects demonstrated in China. And the vapor compression one, that's 10 megawatt, and the absorption one, each unit, that's 45 megawatt. And we have capacity 240 megawatt for the project. We could upgrade waste heat from a thermal power plant, steel industrial, chemical industrial, or cement industrial. And also we need some distributed waste heat utilization with various novel equipment like PCM thermal storage. So we developed, or there is a huge demand in the future for steam generation. So we are happy that we generated this kind of heat pump to upgrade 80 degrees to get the high pressure vapor, steam vapor. And now we consider to use air source heat pump to produce 80 degrees hot water. And then we're using vapor compression compressor to produce steam. And now we have very successful work. So in this case, we could get a COP between 1.5 to 2. So in the ambient temperature, try to absorb heat from ambient, upgrade to 120 to 150 degree temperature, but you output steam. And now already demonstrated for 1 year. So we would like in the future, try to use this kind of air source heat pump for steam generation to replace coal-based boiler or natural gas-based boiler or electric boiler in China. So it's a kind of that now everything try to be electrified. So now we have one possibility to using heat pump to get heating electrified and with high efficiency and less payback period. And also we developed some valuable fact absorption chillers to get more high efficient uses of waste heat, and also developed silica gel water absorption chillers and try to use very low temperature waste heat for cooling. And it could be used for the data center cooling. And also, we need to consider network utilization of waste heat. So we need the match of the temperature. So consider heating source and demand, and then we consider what kind of vapor compression system or absorption system or adsorption system should be used. We need a very good basis to using pinch analysis and to get some TQ analysis and try to get optimization for the real waste heat utilization system. And for the low grade waste heat uses, whether it's heat to electrical, sometimes heat to electrical could be important if you do not have any kind of customer for heating or cooling. In this case, only thermal to electrical, using organic Rankine cycle, for example. But mostly we could have heat upgrading. In this case, heat upgrading and using the heat pumps, whether it's a vapor compression or absorption, or we're using heat to cool, just using adsorption system to make cooling, or we're using thermal storage. And then for the off-peak, or try to take thermal storage in the tracks, and then by just by track cars, and then to move the thermal storage unit for the customer. It's a kind of transportation. So this is all supported by our 13th five-year project, the National Key Research Project, sponsored by the government, and it's 75, yeah, 70, no, that's a 50 million RMB yuan. That's a big project that we collaborate with the industry and to demonstrate the whole project. And what's important for us is to also to produce at the last book, so called energy network uses of low grade waste heat. So That's all for my presentation. Thank you very much.